So this is problem number 2 from the 2022 AP Calc AB free response set. This is a problem that deals with area and volume. So they give us two functions, f and g. So f is defined by this logarithmic function, and then g is defined by this quartic function. They have shown us the graphs of f and g. It says shown above. I had to just kind of fit that on my screen below here. So we do have to kind of be able to identify which one of these is f of x and which one is g of x. Well, a logarithmic graph, and you might recognize this as a horizontal translation of just the natural log of x, 3 units to the left. This top graph has the shape of the logarithm graph, and then this bottom graph is the one that's changing directions a little bit more often, like a quartic function has the potential to do. So you do have to establish which one of these is f of x, which one is g of x. So f of x is within the places where we have a region between the graphs. F of x is the top curve, g of x is the bottom curve. They give us the intersection over here at -2, but then they don't tell us what the intersection up here is. They just tell us that that intersection is labeled as capital B for a positive value of B. So what I did up front here is I just graphed these on my own calculator, and I found the intersection through the calculate menu. So the value of capital B, it's irrational, so I know that I'm probably going to have to base more answers off of this value. So I don't want to round this off to 0.782. I'm just going to take all of the accuracy that the calculator provides me with there and go through the pain of typing that into my calculator anytime I need it throughout the rest of the problem. What we're asked to do in part A is we're asked to find the area of the region between the graphs. So if you think about what we mentioned a few seconds ago, when we have this space between the graphs, the top curve is always f of x, the bottom curve is always g of x. So if we took a vertical slice of that region, the top of every vertical slice, the top y value is given by f of x, and the bottom y value is given by g of x, and then the width of that slice is some tiny, tiny difference in x. So the approximate area of the slice, if we treat it like a rectangle, would be height times width. Well, if we wanted to add together a bunch of those slices' areas to find the area of the overall region, by definition, a definite integral adds together infinitely many products like this. So we can go ahead and integrate that expression in its limiting form. The delta x turns into a dx. You notice I'm just continuing to use the capital B here when I write this integral. You definitely have to list limits of integration on this integral, but you don't have to write this over and over and over again. As long as on your page you show the greater that you found that at some point, and you've defined B to be approximately 0.78, whatever the rest of that stuff is, you can just continue to refer to it as capital B throughout all of your work that involves that value. But when I do that integral on the calculator. So here's my calculator input. The one thing is, now if you, no matter what type of calculator you're using actually, TI-83 is what I have on my computer. If you have a TI-83 or a TI-84, the one thing that I would be concerned about students omitting would be this set of grouping symbols right here. G of x is multiple terms. We need to make sure that we subtract all of g of x whenever we do that integral. You see I took a little bit more accuracy than what I was required to do. So my normal procedure is to round to the third digit past the decimal. I know that this was an irrational value, and I just based another calculation off of it. And because this was a 5 in that spot, I just thought, well, I don't lose points if I am more accurate than I need to be. So I just kind of took that decimal a little bit beyond where I needed to go, just in case there was a little bit of a loss of accuracy due to, this is irrational, right? There's some digit after the 4. It's not that likely that taking all the digits that I got from the intersection of the calculator is going to throw this off in one of these positions of my answer. But I didn't want to risk it, so I just provided a little extra. You never lose points for doing that, but you lose points if you don't go far enough. Part B says that between -2 and that 0.78, we want h of x to be defined to be the vertical distance between f and g. We're asked, is h increasing or decreasing at the x value of -0.5? Give a reason for your answer. So you can kind of eyeball the graph here. At the x value of -0.5, we see g of x is here. We see f of x is somewhere up here. Is that vertical distance between the graphs increasing or decreasing at that time? I mean, you can kind of eyeball the graphs and try to make a guess as to what your answer is going to be. This obviously wouldn't receive credit if you're just looking and trying to say, well, as I move across my x-axis here, seems like this graph isn't moving up as quickly as this graph is, so I think the vertical distance is going to be getting smaller. That's not going to cut it. You're going to have to do something with derivatives in order to build a conclusion about increasing or decreasing, right? If h is increasing, its derivative should be positive. If h is decreasing, its derivative should be negative when evaluated at negative 0.5. So if h of x is that vertical distance, and we want that distance to be positive, we're going to take the top y minus the bottom y, kind of like we did for the height of that slice back in part A. The derivative of h is pretty straightforward. There's no product, quotient, or chain rule or anything crazy. It's just the derivative of f minus the derivative of g. And then I want to evaluate that at negative 0.5. So when I evaluate that at negative 0.5, these are calculations that I can do on my calculator. You see I used the numerical derivative operation on my calculator to determine what this value was. I got 0.4 for that, and then also what this value was, which I got 1 for that. So that's going to give me a negative result whenever I take the difference of 0.4 and 1. And because h prime of negative 0.5 is less than 0, h of x is decreasing at that location. In part C, we're told that the region here is the base of a solid. Cross sections of the solid taken perpendicular to the x-axis. So that phrase, perpendicular to the x-axis, literally says whatever you have sitting on this base, so you have to kind of envision it coming off your screen toward you, whatever you have sitting on this base, if you cut down into it perpendicularly to the x-axis with a vertical slice, and you removed that sliver of the solid, what you'd have when you laid it out flat is you'd have a square face. So we've got a square face with a tiny little bit of thickness to it. What we need to be able to envision is this three-dimensional cross-section being picked up and replaced back down between the big piece of the solid that sits here and the big piece of the solid that sits here. There's a direct correspondence between the two-dimensional slice that I've drawn right here and colored in green and this edge of the cross-section. This has to fit perfectly back down into the base of the solid. So that correspondence should allow you to figure out what the dimensions of this cross-section are. The height of the slice is what we used back in part A for the height of our rectangular slice. It wasn't three-dimensional back then, and it was top y minus bottom y, f of x minus g of x. Well, if this is a square face, that's obviously the dimension across the bottom, and then the thickness of this is some tiny, tiny change in x, right, delta x. So the volume of one cross-section is going to be height times width times thickness, and since height and width are the same, I have f of x minus g of x quantity squared for the area of the face, and then the thickness is delta x. That's just the area, the approximate volume of this one cross-section. I want to add together infinitely many of these cross-sections volumes. So, like we said back in part A, if we have a product involving something in delta x, and we want to add together infinitely many of those, by definition, that's what a definite integral's job is. So I integrate this expression from the x value of -2 to the x value of b, right? That's where all of the slices that I could have potentially taken are going to range between. It's an integral you can do on the calculator. So again, lots of grouping symbols. You have to take care with them. And I would say the same thing I said about part A. This set of grouping symbols in front of the g of x that has to get subtracted is the one that's probably the most significant. There's an extra set here because I have to square f of x minus g of x. So as long as you're careful with your calculator input there, you should come out to 5.340. I did just do the standard rounding here. I didn't have a 5 in this location, so I didn't really think there was a risk of some issue if I was to round up or round down. So 5.340 for that. The last part of this, in my opinion, is I've already done all of the FRQs from 2022, and I think by far this is the trickiest part of any of them. So they tell us that a vertical line in the XY plane travels from left to right across the base of the solid that we just dealt with in part C. So from left to right, the vertical line is starting over here at -2 and just moving its way to the right. It says the vertical line is moving at a constant rate of 7 units per second. What we want to do is we want to find the rate of change of the area of the cross-section of the vertical line, the rate of change of the area of the cross-section above the vertical line with respect to time when the vertical line is at the position x equals -0.5. First thing that you hopefully catch on to here, this right here, 7 units per second, is the rate at which the vertical line is moving across the base of the solid. That's a rate of change. And what I already had underlined here, rate of change of area, is what we want to find. This is really a related rates problem here worked into the end of this. So the 7 is the rate of change of x with respect to time, and we are moving from left to right, so the rate of change is going to be positive 7. We're asked to find the rate of change of the area of the cross section for our solid with respect to time at the x value of negative 0.5. Think about what the area of the face of that cross section was from back in part C. Now I know back in part C we were ultimately finding a volume, but this right here is the area of the face of one of those cross sections, right? Height of the square times the width of the square. So f of x minus g of x squared would be the area of the face. We don't have to take into account the delta x here. So here's my equation for area. I want to find the derivative of area with respect to time. So I take the derivative of the left side of this with respect to t. I also take the derivative of the right side with respect to t. And when I do the derivative of the right side, I am going to have to do a chain rule. So I multiply by the exponent, subtract 1 from the exponent, inner function stays here. And then I need to multiply by the derivative of f of x minus g of x, but I need to multiply by the derivative with respect to time. So the derivative of f of x is f prime of x, but since x changes over time, there's a little chain rule, and I'm doing my derivative with respect to time, keep in mind. There's a little chain rule that I have to finish off here. I have to multiply by the rate of change of the inner function with respect to time. Something similar happens with g of x, right? The derivative of g of x is g prime of x, but since I'm really doing my derivative with respect to time, and x changes over time, there's another little chain rule necessary to finish off there. So I multiply by the derivative of the inside function once again here. So weird derivative. Haven't seen anything quite like this in many free response questions, if any. And then we want to evaluate this at negative 0.5, right? So we want to evaluate this at the x of negative 0.5. So I toss negative 0.5 in place of all my x's. I do need to use my calculator to figure out what this is and figure out what this is, right? Your answer doesn't have to be simplified, but it can't depend on f and g. Now back in part B, we found f prime of negative 0.5. It was that 0.40000. If I click back to it, see it from the calculator input here. Right, so that 0.40000, and then right at the end we have a little bit at the very end of that decimal. But f prime of negative 0.5 is 0.4. G prime from that same part of the problem at negative 0.5 is 1. And then dx dt, you see where my 7s work their way in. And then if I evaluate this on the calculator with negative 0.5 going in place of this x for this calculation, and negative 0.5 going in place of both of these x's. And again, be careful with your calculator input here. If you aren't careful, when you put negative 0.5 in place of the x that's here, if that negative 0.5 is not in parentheses and you raise it to the 4th power, calculator is going to follow the order of operations, give you a negative result, but you should know when you raise a negative to an even power, you're going to get a positive result. So be careful with calculator input one more time. And what you should end up with for your final result there is negative 9.272. I don't think it asks for units or interpretation or anything, so definitely kind of weird. Again, in my opinion, the toughest part of any one of the 2022 FRQs. Hopefully this has helped you come to understand it to a certain extent.